So, back in 2004, a couple of engineers at Google published a paper that, and I'm not exaggerating here, would completely change how we compute things at a massive scale. It wasn't about some flashy new product, but a programming model, a really beautiful abstraction that was inspired by some old ideas from functional programming. It was called MapReduce, and it was basically the key that unlocked our ability to process the internet's insane data explosion. All right, let's dive into this foundational paper and see what all the fuss was about.
To really appreciate the genius of their solution, you have to understand the sheer scale of the problem they were up against. Google's whole mission is to organize the world's information. But that information was growing at a terrifying rate. They were literally drowning in raw data. Crawled web documents, web request logs, you name it. Their existing systems were just completely buckling under the strain.
And when I say drowning, I mean it. The input data for just one tiny part of their production indexing system, the thing that actually builds their search results, was over 20 terabytes. Just think about that. Trying to process that much data in a reasonable amount of time was becoming a pretty much impossible challenge.
So how'd they solve it? Well, not by building an even more complicated system. They actually went in the complete opposite direction. They made it simpler. They came up with a new model that boiled down these massive, messy computations into just two really elegant steps, and they got the idea from the map and reduce functions you find in languages like Lisp. This was the big question they had to answer. See, the actual computations themselves, like counting words and documents, were pretty simple, but the code to do it was buried under all these layers of complexity, just to handle spreading the work across thousands of machines, dealing with failures, and balancing the load. What they really needed was a way for their programmers to focus on the what, the simple logic, and let a clever system handle the how. Okay, so the first step is map. The best way to think of this is the divide and conquer phase. The map function's job is to take each individual piece of input, let's say a single document, and just process it to spit out a bunch of intermediate key/value pairs. So if you're counting words, the map function reads a document and just generates a stream of pairs like, V1. Cat1, Sat1. Simple. And the second step is reduce. This is the bring it all together phase. The system takes all those intermediate pairs that have the same key, like all the pairs for the word cat, and it hands them over to the reduce function. Its only job is to merge those values. So in our word count example, it just adds up all the ones to get the final count for the word cat. All right, let's make this even simpler with a great analogy. Imagine you're at a potluck and you're trying to make a giant fruit salad. The map phase is like giving every single person a piece of fruit and one simple instruction. Chop it into bite-sized pieces, right? Everybody's working in parallel on their own little piece of fruit. The reduce phase is when one person's job is to collect all the chopped apples from everyone and put them in a bowl. And another person does the same for all the chopped bananas, and so on. So map is distribute and process. Reduce is collect and combine. See? Super simple. Now, that two-step idea is pretty slick on its own, but the real magic was in Google's implementation. They built this whole runtime system, kind of like an automated data factory, that took a programmer's simple map and reduce functions and just automatically ran them in parallel across a massive cluster of thousands of regular, everyday computers. And inside this factory, there are basically two main roles. You've got one master process, and it acts like the factory foreman. It hands out assignments, it keeps track of what everyone's doing, and then you have hundreds or even thousands of worker processes. These are the employees on the factory floor. They just grab a task from the foreman, either a map or a reduce task, and they get to work. That's it. And this quote from the paper just perfectly illustrates the magic. It says it all. As a programmer, you suddenly didn't need to be an expert in complicated distributed systems anymore. You just wrote your two simple functions, and the MapReduce library took care of all the really hard stuff for you. It was an absolute game changer. Let's talk about one of those messy details, failures. On a cluster of thousands of machines, you have to just assume that machines are always failing. It's a fact of life. Now, in the old world, a single machine failing could bring your entire computation to a grinding halt, and you need a human to go in and fix things. But with MapReduce, the master just periodically checks in on its workers. If one doesn't respond, the master just goes, "Okay, you failed," marks it as dead, and reassigns its task to another healthy worker. The whole job just continues on seamlessly. No pagers going off in the middle of the night. Okay, so the theory sounds great, it's beautiful, but how did it actually perform in the real world? The paper details a few tests, but let's look at a big one, sorting a massive amount of data. They ran this on their cluster of about 1,800 standard off-the-shelf machines.
And believe me, they weren't sorting a little grocery list. The data set for this benchmark was 1 full terabyte. That's 1,100,000,000 byte records. This was a total monster of a job, and it was designed to push the system to its absolute limits.
Now, what's really interesting here is how it highlights a subtle but huge problem you run into with large-scale computing, the straggler. A straggler is just one machine that's running unusually slow for some random reason. Maybe it's got a flaky hard drive or some other process is hogging its CPU. The problem is that one little slowpoke can hold up the entire job.
I mean, just look at that difference. Without a way to deal with stragglers, the whole job took 44% longer. So MapReduce solved this with a really clever trick called backup tasks. As the job is getting close to finishing, the master proactively launches backup copies of the last few remaining tasks. Whichever one finishes first, the original or the backup, wins. Problem solved.
But what about, catastrophic failure? To test this, the engineers did something pretty incredible. A few minutes into that massive terabyte sort, they deliberately killed 200 of the worker machines. Just poof. That's more than 10% of their computing power, gone in an instant. And here's the stunning result. The system barely even flinched. The master noticed the workers were gone, calmly rescheduled their in-progress tasks to other machines, and the entire job finished just 5% slower than if nothing had happened at all. This proved the system wasn't just fault-tolerant, it was incredibly resilient.
So what happened next? Well, the impact of this paper is frankly hard to overstate. This wasn't just some academic exercise. It immediately transformed how Google operated, and it went on to ignite an entire industry. Internally at Google, the benefits were immediate and profound. They rewrote their entire production indexing system as a sequence of MapReduce jobs. The new code was just dramatically simpler, smaller, and way easier for new engineers to understand. For instance, one piece of the code went from 3,800 lines of really complex C++ down to just 700. It let them innovate at a speed that was just impossible before. But the story definitely doesn't end inside Google. Inspired by this 2004 paper, developers in the open source community created their own implementation, which you've probably heard of, Apache Hadoop. Hadoop basically took the MapReduce model and made it accessible to everybody, and that really kicked off the big data revolution, powering countless companies and technologies that we all use today.
So here's the real takeaway from all this. MapReduce won the day not by adding more complexity, but by brilliantly subtracting it. It gave developers a simple, powerful abstraction that hid all the messy details and let them focus on what they actually wanted to compute. And it leaves all of us with a really powerful question to think about. What are the complex, tangled problems we're facing today that are just waiting for someone to come along with a simpler way of